Hello, everyone, and thank you for joining us for our webinar today. We're going to be discussing HBM and 2.5D design. This is actually a replay of something we did live at the Computer History Museum a few weeks ago. We had a very good crowd there and a lot of interest. So we've turned it into a webinar to reach a wider audience. I'd like to start now by introducing Kevin Tran, the Senior Manager of Technical Marketing at SK hynix, who's going to talk about the memory portion of the HBM stack.
Thanks, Mike. Hello, everyone. Thank you for your time in joining us. So a little bit background about SK hynix and why we came to developing the HBM technology. Well before the 2011 timeframe, we had a lot of our customers were looking for the next generation of memory subsystem devices, and at that time, most of them were concerned about the memory wall. Some of you might be familiar with the low bandwidth and the lack of scaling and performance, as well as the high power consumption per I/O pin. So we saw a tremendous value with TSV or through silicon via types of technology like the HBM, and have been developing the HBM product since 2011. As some of you may know, we went into production of the first generation of HBM Gen 1 back in 2015. And so we had a lot of learning opportunities to fine-tune our development as well as our testing of the program. So today we're very well aligned with the industry as well as our customers in terms of the HBM product, their requirements, as well as the issues that customers are concerned about. So we're confident we will deliver a second generation this year that will address almost all of the industry's requirement or bandwidth memory wall solutions issue. So here's a bit of information about myself. I won't go over them, but I did leave my contact information here just in case if any one of you wanted to get in touch with me for more information. Due to the time constraint here, I won't be able to go really into the deep or in-depth information about the HBM device, but please contact me if you have any questions. So this slide really sums up the overall reasons or benefits that customers see in an HBM technology, mainly for the bandwidth as well as the consumption and form factor, versus some of the existing or most of the existing memory technologies here. This figure here shows the bandwidth comparison between the first generation and subsequently the second generation of HBM device with a graphics, GDDR5 and a DDR type of solution. You can see that with the first generation of HBM device, we're able to provide 128 gigabyte per second of raw bandwidth from the DRAM. This is one single device versus the other ones that you can see here on the GDDR5 and DDR. With the second generation of memory devices, HBM, we're scaling this up to 256 gigabyte per second of bandwidth. This is a tremendous bandwidth improvement over the existing commodity DRAM. Looking at this figure, the power consumption for a 128 gigabyte per second implementation in bandwidth, comparing with various technologies here, this is an overall 60% of power consumption or reduction versus a GDDR5 solution. Now, in most of our customers' next generation systems, they're looking at terabytes per second or even more than that in high performance computing and also in some forms of networking. And in order to achieve this type of bandwidth using existing DDR4 solutions, you would need 40 pieces of DDR4 modules running at 3200. As you know, this solution here, even if it's available today, would take up a lot of your board space. And to implement this using discrete DRAM solutions on DDR4, you would require 160 pieces of external DDR4 memory running at 3200. This is a tremendous amount of routing that you have to do on your board. Now compare this to a much more elegant solution using an HBM technology. You get 1 terabyte of bandwidth with just 4 pieces of HBM2. All of this would fit into a 50 by 50 millimeter square package with an ASIC. So overall, due to these benefits, all of our customers are adopting HBM in a wide variety of applications. Some of them I show here. These are the main applications that we're seeing HBM being adopted. The first one is in high-performance computing and server, where the HBM provides a really low power or power-efficient bandwidth solutions for the processor. Of course, this is an HBM, high bandwidth memory. It's not a high-density memory. So for a added or extra capacity, the processor would still go out to external DDR type of modules for that capacity, but it has right in the package a very efficient way to get very high bandwidth. In networking and graphics, the HBM acts as a frame buffer or a data buffer on networking line cards. And again, HBM can also be used in some cases, if customers have the IP, they can do header processing in the HBM as well. We're seeing design wins with client or notebook space in the high-end application. And again, this is a very high bandwidth, low power, very energy efficient solution. We're right now currently working with some mobile processor partners to enable the HBM for mobile application where they're doing a 3D type of stacking with the HBM technology. Here's an overall overview of the HBM architecture. JEDEC defines the HBM to have 8 memory channels. What I show here is 4 slides of DRAM. I'm not showing the base die. Overall, each slide in this implementation has 2 channels. With the HBM Gen 2 from SK hynix, we support the pseudo-channel mode. So each channel here is divided into 2 sub-channel or pseudo-channel. Each pseudo-channel have their own separate I/O, independent I/O. The command and address are shared. So what that allows your memory, if you design your own memory scheduler, to really ping pong back and forth between the different pseudo-channel and really maximize the data that you are pumping through your DQs. We understand that the HBM is an in-package type of memory, so quality and reliability are of the utmost importance to our customers. So built into the HBM are a lot of technical or technology hooks that allow us to ensure high quality and reliability when before and after the assembly process. We're able to do cell repair to the HBM just like external memory. The HBM supports error correction code. We also provide our customers with our own programmable BIS engine as well as the built-in self-stress test. What this does is it allows our customers to use our IP to identify any fault, any failure on the HBM device, and allow them to repair. I'll talk about the repair in the next few slides. This is an example of the repair that you can do on the HBM device. Also, SK hynix come up with a proxy package idea where we bring out the pins on the HBM through a GDDR5 package. What that allows us to do is to ensure that we're having yield that's aligned with our manufacturing targets and also that the quality of the device meets our expectations. This is an example of the test and repair capability that the HBM offers. All of this is done through the IEEE 1500 interface. So all of our engineers in the industry are very well familiar with this protocol. You're able to repair the cell in the HBM. Also, any of the micro bumps on the HBM that is identified to be faulty, you are able to do that. I won't go over the procedure on how to repair. This is in the HBM spec. You can contact me and I can provide you more details on how the repair is done. This is the product lineup of HBM from SK hynix. We provide 3 flavors of HBM in terms of density. Each of them are based on an 8 gigabit mono die. So stacking 2 high, 4 high, and 8 high would give you effectively 8 gigabyte, 4 gigabyte, and 2 gigabyte densities. All of these will support 1024 IOs, and so you're able to get or extract the maximum 256 gigabyte per second of bandwidth per device. And that is all I have prepared for my part of the presentation. Again, any questions, please text us or contact me through email. Thanks. Thanks, Mike.
Okay, thanks, Evan. Okay, so next we'll hear from Paul Silvestri, who's the Director of TSV Product Development at Amkor, and Paul will tell you a little bit about the substrate and the assembly part of this of the system project.
Hello, this is Paul Silvestri at Amkor Technology. The Amkor portion of the supply chain is indicated here by this graphic in yellow, and what Amkor provides is the post-foundry processing of ASIC and TSV bearing interposer wafers and performing the assembly and testing of integrating these devices into an HBM 2.5D system. The overall process steps are highlighted here. Of course, our process starts with a TSV bearing interposer wafer, 300 millimeter device, and Amkor performs the front side bumping and the backside reveal of the TSVs, followed by metallization. Additionally, the logic or ASIC wafer is provided to Amkor, and Amkor provides fine pitch copper pillar bumping and wafer probe if required at the Amkor facility. Similarly, the HBM devices are received into Amkor, usually received within a tape and reel form, and these are already tested at the supplier, in this case SK hynix, and those are received into the Amkor facility and prepared for assembly. And then finally, the last step is to bring all of the wafer components and memory devices into an assembly area where we perform assembly, interim test if required, and complete the final assembly. Amkor's packaging platform consists of a very flexible process flow that supports our customers' product requirements. The most common form of assembly is what I will refer to as a 2.5D chip-on-substrate assembly platform. And this process begins with the standard flip chip substrate. The interposer die is attached to that substrate, followed by the top die, whether it be an ASIC, logic, another logic device, or an ASIC plus a memory combination. After those die are assembled to the substrate, the final assembly can take place where we would place spheres and a thermal lid onto the device. Other platforms that Amkor can support, depending on your product requirements, is a 3D TSV assembly. This is typical applications would be a logic plus a memory configuration, or just a pure memory, a memory integration where we're bringing all memory together in a tier-to-tier fashion using a chip-on-substrate platform. And then, of course, the last methodology that is deployed is a chip-on-wafer flow, where the typical application is starting out with a interposer wafer, populating the die sites on that interposer wafer with logic and memory, finishing up the processing by overmolding and mold grinding the device itself, and then assembling that particular module shown here in this red box down to a substrate, and then completing the final assembly. This process flow is, of course, compatible with 2.5D interposer style solutions as well as 3D tier-to-tier type of assembly stacks. The general process flow at Amkor is we start out with a TSV wafer that is fabricated by a foundry. And then, of course, outgoing from that foundry, the foundry can either perform the wafer sort or the OSAT. In this case, Amkor can perform the wafer sorting. After incoming test is completed, the wafer enters into what we call a middle end of line or MEOL flow. And that MEOL flow consists of front side bumping to create on the interposer case to create a nickel gold pad. on a 3D case to create a fine-pitch copper pillar bump. After the bumping is completed, it enters into the MEOL1 step, which the MEOL1 consists of processing the backside of the wafer to remove bulk silicon and expose that TSV from the backside. After that TSV is exposed from the backside, it can now enter backside bumping, and we can perform RDL and C4 bumping in the case of 2.5D, or again create another pad for the case of 3D. After the backside bumping is completed, the wafer is then diced up and made ready for the assembly step. And then the assembly steps would be the methodologies I explained in the previous slide. Testing is an integral part of our process flow, and the Amkor process flow is flexible so that we can perform interim steps throughout the assembly flow in order to test subassembly modules as required by the customer. The overall process flow for a 2.5D chip on substrate is shown here, and again, the lower left corner here where my cursor is moving is where the substrate is prepared and brought into the assembly area as it's prepared to receive the interposer die. The interposer wafers itself, again, as I had explained previously, goes through the MEOL and front side and backside bumping process, revealing of the TSVs and dicing up of the individual die. Once those die have been diced up, the die attached to the substrate can commence. After the interposer is attached, a similar process flow is the logic device or the ASIC device can be wafer sorted at Amkor, fine pitch copper pillar bump, thinning down of the wafer in order to achieve a targeted device thickness as specified, and then dicing of that unit before it can be assembled onto the interposer and substrate assembly. After everything on the logic side is completed, this subassembly module can be presented for a test. We can go through and test the functionality of the ASIC device, going through a functional test and a system level test, and then that unit is returned back to the assembly line where the memory device can now be attached to that system. For the memory device, of course, the device is received at Amkor in a tape and reel fashion. The die are prepared and inspected to get them ready for assembly, and then the memory devices are attached onto the interposer adjacent to the logic device and on top of the interposer device. After the memory device is completed, the final assembly can take place where we can attach the spheres, any backside caps, and the thermal lid solution, whether it be a ring, a stiffener ring, or a single piece lid. After that final assembly is completed, the device can be presented to a final test, another system level test, and then can be dispositioned out to the customer according to the customer's instructions. Just some overall product architectures that Amkor has been seeing throughout the industry. The key here is shown here as this color-coded key. The green color is the substrate, the grayish color is the interposer, the light blue would be a typical logic, and the blue color would be the HBM devices. Many of these architectures look very similar. They're bringing the HBM device close to the logic device in order to have the optimal power per bit threshold. And then depending on the customer applications, sometimes on the graphics side, in the networking side, et cetera, we can have varying numbers of HBM devices that we want to have integrated into the assembly. Amkor's TSV production readiness, of course, we have a production line installed within our manufacturing facilities. Our yields that we're seeing on production runs is exceeding 98% with CPKs greater than 1.3, and all of these systems are under SPC control. The bumping and assembly is in a similar state. We are running production today with yields over 98%, and of course we're leveraging our existing high volume manufacturing assembly and bumping assets within Amkor. And our product qualifications that have been completed on the 3D side, we've completed over 3 product qualifications with these environmental conditions, as well as over 4 2.5D interposer HBM products with these environmental conditions here. And with that, if there is any additional questions you may have for Amkor, I can be reached at paul.silvestri@amkor.com, and of course be found on LinkedIn. Thank you.
Thanks very much. Yeah, and I'll just remind everyone, we are seeing some questions coming in the chat window, so feel free to add your questions there. We will address them. So next, we're going to hear from Bill Isaacson, who's the Director of ASIC Product Marketing at eSilicon. And Bill is going to talk about the actual ASIC that's part of the system, as well as the HBM PHY and the overall strategy around assembly and test for the complete device.
Thank you, Mike. So today I'm going to be talking about the Mosaic program at eSilicon. Mosaic is the name that we use to describe all of our 2.5D activity. It stands for Modular Z-Axis IC, and today I'll be focusing on its application to HBM. First, just a little bit of history, the background of eSilicon as it relates to 2.5D. We started our development on 2.5D programs in 2011. We did that because we saw the promise of the technologies, that we could see higher degrees of integration, potentially lower development costs, higher performance, and lower power compared to a monolithic ASIC. In that time, we did a degree of R&D work, test chips, and then production chips to get us into a situation where we can service our customers today. You can see in the chart here, 2014 is when we started limited production projects with our customers. By 2015, we had completed 7 individual test chips that were focused on things like looking at the evaluation of materials for interposer, looking at the different assembly processes in the industry, looking at qualifying the technology, and also qualifying our IP. Today, where we stand, we have customer programs at 28 and 14 nanometer that are targeted for high volume production. Now, to enable ASIC with our customers, the first thing that we needed to do is have an IP ecosystem for those ASICs. And when we looked in the industry, we found there were no PHYs available, so eSilicon developed one. This is a block diagram of our PHY. It looks a lot like other memory interface PHYs on the market, but has some unique features specific to HBM. Starting from the left side, you can see IEEE 1500 wrapper, which is giving us the test interface to be able to communicate between the PHY and the HBM2 memory. You also see the bump repair. So this is the logic that actually goes in, detects if we have a broken trace or a broken micro bump between our ASIC and the HBM memory, and then starts the process of remapping it to a known good trace or known good bump. And then we have the PHY logic, the part that actually does the timing, the serialization of the data. What is unique here is that this is 1,000 bits to be compliant with the HBM standard. And then finally, we have our I/O sitting out on the edge. This entire PHY is delivered as a hard macro to our customers. It's also integrated as a hard macro into our ASICs. Now, with the PHY, we started designing these with HBM1. That's available, it's silicon proven. We've since moved on to HBM2, propagating our technology out to as many nodes as possible. Today we have 28 HPC that views are available. The test chip for this is in the foundry today and will be very quickly silicon proven. We have 14 nanometer where models are available today. The test chip for this technology goes out in May, and our evaluation of the silicon will be complete in September. And commensurate that will be the final models. And then right behind 14 nanometer, we're also developing 16 nanometer. So we've taken this PHY and very quickly propagated it out to many different technology nodes. Now, once we have the PHY, now what we need to do is wrap that IP with our ASIC services, but also with 2.5D interposer design and package design services. This slide is really focused on the interposer aspects. As a company, we have in-house interposer design capability. For our customers, we will design and build the interposer sitting on top of the package. We will design that for manufacturability. We have an in-house signal integrity and power integrity team. So the signal integrity aspects of interposer are taken into account as we design it. We have the ability to look at the thermal integrity of the overall system, as well as the warpage of the overall system, and make sure that we're going to have something which is going to be flat and reliable for our customers. Now, around 2.5D, from a production standpoint, what eSilicon is offering is either the acquisition of the die going into the package, if they are external from us, or building the ASIC, the assembly of all of those die onto interposer in package, the test of that packaged up solution, and then delivering to our customer a final tested yielded device. Now, to talk a little bit about our capabilities, this slide is showing some of our temperature analysis capabilities, where we're showing different cuts through the package and different environmental conditions. Something that we can do ahead of time is important in these systems because the die that are in these systems do tightly thermocouple with each other, and that means that we are very concerned about how we're going to dissipate heat inside of the system. We also have the ability to look at warpage in simulation. We're doing this because we are having large interposers, which are very, very thin pieces of silicon. They do not have a lot of structural integrity, so we know that they're going to bend. And so controlling that bending is one of the key concerns when we're building a 2.5D based system. Here we're looking at some of the simulation capability to be able to look at what type of warpage we would expect from a customer-specific configuration before we commit it to silicon. Now, along with being able to build the interposer, we also have to worry about the testability of the overall system. This slide is trying to capture both how do we test the different components and when do we test them in production. Maybe moving from the top right to the left, we have the ASIC sitting here. Most of the ASIC is tested just like we would any other ASIC. It's AC and DC scan, it's memory BIS, memory repair, JTAG, and then any IP-specific test vectors that are required. What is unique is embedded in the ASIC is the ability to test the connection to the HBM and initiate tests with the HBM as well. So for the connectivity here, we have the ability to initiate BIS and the repair through the IEEE 1500 interface. That's the ASIC telling the HBM, please initiate test and tell us the results. We have the ability to check the connectivity between the two chips using JTAG. We also have the ability to make sure that this link is running at speed. That's a performance test performed by the miser. And then finally, we have the ability to repair any broken links on the interface. And then finally, on the HBM, we do bring out the DA pins, which are unique to the HBM memory, so that we have an ability to debug the HBM in system using some of the direct tests. Now, from a production test standpoint, the HBM are provided as known good die, so we're not doing any additional tests at a wafer sort level. We are testing the ASIC with sufficient coverage to make sure that we've got high yield of the final system. And then at final test, we are running all the production tests on the HBM, as well as all the production tests on the ASIC. And that's how we're ensuring that we're providing our customers with high coverage, well-tested parts. Now, with these capabilities, what we've been able to do is go out and engage with customers. Up here, I have 4 examples of customer engagements. Top left is a project that we did with the customer to evaluate different interposer technology. In this case, we were looking at organic interposer and getting a look ahead on the technology. You can see in the middle a large die communicating out to 4 HBM1 stacks sitting on top of the organic interposer. That led to some initial production programs. So this is a 28 nanometer design that we've done. 20 nanometer ASIC in the middle, communicating out to 4 HBM1 stacks. This sits on top of a silicon interposer. So this is an actual device that's been built. And that led to actual production programs that will go to high volume production with our customers. Here's an example of a large 28 nanometer ASIC talking out to 4 HBM2 stacks sitting on top of a silicon interposer. And here's an example of a 14 nanometer ASIC sitting on a silicon interposer communicating with 1 HBM stack. So the messages that we would like to leave you with is, from an industry standpoint, we see that the transition to high bandwidth memory has happened. Our customers are now comfortable in the memory technology. They're comfortable in the interposer technology. They're now coming to us with RFQs and engaging with us on actual programs. So we see very strong adoption. And we're seeing that because HBM is a JEDEC standard. It's available from multiple sources. It's very high bandwidth compared to the alternatives. It's very low power for that bandwidth. And if you look at the alternatives to how you were to get to this type of bandwidth, it's also lower price. So you win on all fronts. We've been doing HBM production-based designs since 2015, with production starting in 2016. We've leveraged our past experience, all those 5 years of R&D work and test chip work, to be able to get ourselves into this position. As I said, we've completed multiple test vehicles in the past. And finally, what this has allowed us to do is provide to our customers a complete HBM solution where we are providing the PHY IP, the ASIC design, the sourcing of all the materials, the manufacturing, the test, and providing to our customers a final tested packaged yielded unit. That concludes my presentation.
Okay, thanks a lot, Bill. So next we'll hear from Brian Dellenbach, who's the president of Northwest Logic. Brian's going to tell you about the controller IP for the HBM design, which is a critical piece of IP enabling the system to work properly. Brian, it's all yours.
Great, thanks, Mike. So I'm going to jump right into this here. So my name is Brian Dellenbach. I'm the president of Northwest Logic. To just tell you a little bit about Northwest Logic, we're located in Beaverton, Oregon. We've been in business for 20 years. We focus on providing IP cores for memory interfaces, PCI Express, and MIPI. Our focus is on providing controller cores. We don't provide PHYs. What we do is we integrate our cores with PHYs, such as the eSilicon PHY for HBM. So that's what we're all about. Of course, with this presentation, what I'm going to focus on specifically is our HBM controller solution. So our HBM controller solution is shown here. So when we are currently supporting 7 different designs. We have 3 test chips underway, and as part of that, we have seen and engaged with a very broad variety of customers. The number one thing that customers want when they're engaging with us is they want to ensure that we've got a solution that's flexible enough to meet their specific needs for their application. So what we have done is we've put together a very flexible solution. That solution consists of not only a configurable controller solution, but a series of add-on cores, which I'm going to talk about in the rest of this presentation. The second thing that they're very focused on is having a very high-performance solution. They want to make sure that this solution on a clock-by-clock basis is doing the absolute optimum. So I'm going to be talking about that a little bit. The third thing they want is they want a full solution. They want to make sure the controller is fully integrated and proven to work with the target PHY. So we've done exactly that. We've collaborated with eSilicon. We've taken their PHY, fully integrated with the controller, and so when we deliver the controller, that integration is all done. Customers don't need to do any of that integration, and we fully support that integration with the support of eSilicon. Last thing that customers want is they want a fully verified solution. So what we've done is we've worked very closely with a variety of memory models. We use the memory models from Avery. Chris will be talking about that in just a second. Those memory models are very good for providing a comprehensive verification of the integration of the controller, the PHY, with the memory. We also, of course, use the memory models directly from the memory vendors, such as SK's memory model. Our solution has been validated in hardware with HBM Gen 1, and as I mentioned, we have several designs underway. So those are the key top-level points. What I'm going to do now is talk a little bit more in a little bit more detail about some of those items. Okay, so I mentioned we have a very configurable controller. The most common configuration being used is the one that I'm showing here. In this configuration, we have, for each channel, we have 2 controllers. This is called the dual controller configuration. There's basically one controller for each pseudo channel. HBM is divided up into 8 128-bit channels. Each of those 128-bit channels is divided up into 2 64-bit pseudo channels. So in this situation, we have 2 controllers, one for each pseudo channel, and then the user can interact directly with each of those 2 controllers. We have other configurations where there's a single controller controlling both pseudo channels, etc. The bottom line is we have a very flexible controller that can be used in a number of different configurations that can maximize the performance and minimize the overall gate count depending on the specific customer requirements. This particular configuration runs at half rate, which means it runs at 500 megahertz instead of the 1 gigahertz memory clock. So that, once again, minimizes power consumption and also eases the closing of timing. I've mentioned the need for memory efficiency. So because we've engaged with such a broad variety of customers, what we find is each customer has their own unique access pattern that needs to be supported. So what we have done is we have done all the tricks in the book that are available with HBM to maximize performance. Single bank refreshes, simultaneous row and column command, command interleaving, et cetera, optional request reordering. All the various tricks are there. So one of the things is, as customers come to us, they typically have very specific patterns that they need to make sure are optimized. We deliver evals to them to enable them to do that. We will also put together sequences that will show them the performance they can get. And after doing this over and over again, we have achieved a very optimal controller for maximizing performance. So if you have any questions about that, please contact us, and we'll be happy to help you understand the performance that you can get for your specific design. So not only do we provide a controller, but we have, as shown here in blue, we have a whole series of add-on cores. So many customers want to have their logic directly interact with the controller, and that's just fine. But other customers want to have a multi-port AXI-based system with reordering, et cetera. So what we do is we configure this overall solution specifically to the customer needs, deliver it to the customer configured to those needs, so that minimizes the logic needed. There's no extra logic. Only the functionality that's needed by the customer is delivered to the customer. The other piece that we have is we also have a very comprehensive memory test capability. This provides a system-level memory test solution where the solution will actually go and do a series of pattern writes out to the memory and then do reads, and then basically, if there's a discrepancy, basically point those out. So that can be used during a bring-up of your solution, and it can also be used for in-field evaluation. So from an overall status perspective, the controller core, as I mentioned, is fully released. We have 7 customer designs that are in process. Several of those designs have already gone through full place and route, so we have conclusively shown that we can comfortably, on a push-button basis, do timing closure. The core has been fully integrated and validated with the eSilicon HBM PHY. And not only do we have 7 customer designs in process, but we also have 3 controller and PHY chips that are in process. So if you have any questions about this whatsoever, you can contact me at my email and phone number there. And also, please visit our website. There's additional information on our website, and you can, on our website, generate an info request and get full access to all the collateral associated with the core. So that concludes my presentation, and now I'll turn it back over to Mike.
Thanks very much, Brian. Okay, so we're on the home stretch. One more presentation from Chris Browie, Senior VP Worldwide Sales and Marketing for Avery Design Systems. Now we're going to hear about optimization and verification of the HBM system.
Thanks, Mike. In this session, I'll introduce you to Avery Design and our family of VIP, and in particular take a closer look at the HBM. Avery is not exactly a new company. We've been in the VIP business for over 10 years, and we have established leadership in VIPs like PCI Express and NVMe. In fact, many of the attendees today of the webinar, their companies use Avery for these types of VIP already. Our main business is VIP. However, we also have a couple of other tools for most notably some formal-based applications targeting X verification for RTL gate-level SIMs and reset optimization. Our VIP library is pretty comprehensive. We have over 50 titles, and we're adding new ones all the time. Some of our VIPs are actually exclusive to the industry as a whole. like our XHCI, UFS HCI, and our LRDIMM solutions. And specifically of late, the memory VIP has seen a lot of interest and adoption by customers who are looking for native system Verilog models and a number of the unique features that we offer compared to our competitors. Specifically, some things like a memory controller, BFM, and test suites for LRDIMM chipsets and PHYs, and even more novel types of designs like all-flash LRDIMM memory modules. And some of our VIPs, like I mentioned, PCI Express and NVMe, have excellent acceptance by the top companies in the field. We have a lot of IP partners. Obviously, Northwest Logic, eSilicon are two of them, and this helps us keep our VIP leading cutting edge and very, very mature and good capabilities. The flexible licensing model and the compliance test services also are quite important as well. But now let's take a look at HBM specifically. So here we just show the overall test bench architecture for doing SoC or memory controller or PHY verification. So for the memory controller and SoC verification, mostly you would use our HBM memory model and our PHY monitor. The HBM memory can be programmed through its sequencer for backdoor access or error injection, supports scoreboarding. For the PHY verification, this is where you'd use the memory controller BFM to basically drive the HBM command sequences to operate on the PHY dot. Some of the features shared by our memory model and our memory controller model include stuff like dynamic model configuration in terms of setting up the number of channels per stack, density, banks, operating speeds, and timing parameters. Our models support all the HBM commands and modes, as well as the IEEE 1500 port commands and wrapper registers. This means you can test the PHY features like the address word and data word pin remapping types of features. We do support the JEDEC as well as vendor timing models, but the timing model itself is a system Verilog class, which means those values can be modified at runtime, including setting up quick sim modes that sync up with the memory controller, such as from Northwest, as well as the PHY from eSilicon. The HBM memory model has a lot of advanced features like the direct backdoor access to the memory, as well as the memory, the MRS registers and the wrapper registers. We use a sparse memory model implementation, which is efficient runtime memory profile. And we actually have a waveform replay capability that should you find any issues with the memory model, we can replay a waveform and basically resolve any issues quite readily in that manner. We also have other advanced features compared to vendor models, and we'll look at those more in a minute. Just another discussion about the memory controller again. The memory control and PHY models perform the power-up initialization sequence and supports the power modes, all the command sequencing, error handling, and all the 1500 port commands and sequences. And we also support random configuration of the HBM MRS registers, which can test the PHY out in many different configurations as well. So the memory controller can drive the traffic for all the command-to-command timing and functional interdependencies, and help verify the PHY with very comprehensive traffic. The HBM memory model also includes a protocol analyzer tracker, and this is an important feature for really debugging what's happening in the system, what traffic you're driving into the memory. So this would basically show things like, for example, we're showing here the command issue and data burst times for each pseudo channel. And we generate a tracker for each channel, making it easier to easier to debug the situation. The HBM memory model also supports error injection using standard UVM methods such as callbacks and TLM ports. Typically, you can use the various callback points to inject ECC errors and parity errors on read or write, corrupt the data, or change the timing class of the HBM memory. We support over 225 protocol checkers in the model. This includes functional and timing checks. We generate a trigger coverage report to show you what checklist items are actually exercised during a test case. And from run to run, you can merge the results across a regression to get an overall coverage model of the design. And this is actually a very good verification coverage closure measure to make sure that all the key HBM memory protocol checks have been exercised and in the design. Functional coverage is also built into the models and can be extended by the end user. We track a number of key parameters that give a good indication that the basic commands and modes have been covered. Like the protocol coverage, the functional coverage can also be merged across a regression. Now, since HBM is used in high-performance systems, it's very important to closely monitor the memory subsystem for peak performance on memory-intensive algorithms. So we originally got the idea of putting performance metrics into our VIP by looking at memory bus analyzers that are used in the lab. So some credit goes here to companies like Future Plus and Keysight, who we followed very closely in our implementation. So here we've developed a performance interposer in our memory model to allow the user to monitor their design during the critical sections of a test case and actually recognize whether the system and memory controller optimizations are working effectively. We track over 60 performance metrics ranging from utilization to bank and bank group analysis, as well as providing detailed latency for command sequencing. Things like power management shows the active versus power down types and confirms power saving operation. Bank and bank group analysis can help verify that the memory controller, bank group optimizations, and system software page allocations are working correctly. And this looks at consecutive read to write combinations to see how many stay within a bank group. Command utilization also shows the sequencing of the commands and make sure that they're working efficiently. For example, we show the read versus write versus active cycles and even track the dual command mode overlap, which is one of the performance features of HBM. More fine-grained metrics include the from-to command latencies for all the combinations of command sequencing, including within and between bank and bank groups. So by tracking these measures, you can understand not only whether peak performance is achieved, but also understand the worst case and average latencies in the system, which shows whether the system achieves good overall uniform operating performance. Combinations include the column commands like read and write command sequencing, as well as the row commands. In fact, there's over 38 combinations broken down by bank and bank group and axes, and there's a lot of good information that's contained in the reports. But the key is to have very good, well-formulated reports so that they're easy to inspect and learn from. So from the latency reports, you can see whether there might be some abnormalities, which we can identify here in the case of a read-to-write combination between banks. Or even you can look for other cases of command-to-command combinations that either don't occur or are occurring very infrequently. This could actually also give an indication of design bottlenecks or software algorithm issues. So and we also have the ability to set performance triggers, which can alert you when there's a performance metrics which is operating outside of the desired operating range. So I'd like to conclude just by wrapping up on a few points. Our HBM solution targets both memory controller, system on chip, and PHY verification. We offer many value-added features over the vendor models that ensures the closure on functional verification, compliance, and performance on your designs. And finally, that along with our supply chain partners, we bring together the best-in-class technology to ensure quality design results and interoperability. So I'd like to thank you for your time today and turn it back over to Mike.
Well, thank you, Chris. So that concludes the presentation portion of our webinar. Mike Gianfani here. I've been your moderator for this part of the session as well. Again, thank you very much for your attendance.